Great, thanks, Althea, and good morning and welcome. Go Who's! It's a great day. Yeah, let's give it up for the Cavaliers later on, as well as our faculty. So it's my pleasure always to be with you on Saturday mornings. I love seeing old friends and making new. And we have a new friend at More Than the Score, a special guest with us in addition to our faculty members. Craig Benson, who is the Dean of the School of Engineering, is with us today. Dean Benson, can you raise your hand? And everyone give him a welcome. Thank you. And so now it's my pleasure to introduce Jack Stankovic, who is UVA's BP America Professor in the Computer Science Department at the School of Engineering. Jack is also the director of UVA Link Lab, which began with over 24 faculty members drawn from multiple departments who work on UVA's pioneering work in areas such as body sensors, smart buildings, and wireless health. The lab hosts a unique collaborative group of researchers dedicated to solving the most critical problem in our world today. And in addition, they have over 100 graduate students that work with them, so that wonderful combination of faculty and students. Jack graduated from Brown University with his undergraduate, master's, and PhD degrees, and he is the recipient of many international awards, including the prestigious Award for Outstanding Technical Contributions and Leadership from the Institute of Electrical and Electronics Engineering, or it's much easier to say IEEE. At UVA, he was awarded the University of Virginia Distinguished Scientist Award and the School of Engineering's Distinguished Faculty Award. Jack is a frequent speaker and has given more than 40 keynote addresses at conferences and major universities. Please join me in welcoming Jack and his colleagues to More Than the Score.
Thank you. So welcome, everyone, and good morning. I will moderate this panel, and we're going to talk about the Link Lab and the work that we're doing in the Link Lab that we refer to as cyber-physical systems. All right, I'm not going to do a lot of comments, but I want to answer two questions. What are cyber-physical systems? And how did this lab come about in the first place? Okay, so traditionally, engineering disciplines work with the physical world, whether it's electrical engineering, mechanical engineering, civil engineering, and so on. But as technology moves forward, more and more of the solutions needed are software components. And so it becomes necessary for any discipline to address the cyber problem. Similarly, in computer science, most of the work was on algorithms and virtual worlds, but with the advent of smart phones, smart devices, things like Siri and Alexa, smart cities, all of this requires computing to now understand the physical world. So this synergism between the physical and the cyber is incredibly important, becoming more and more important, and it's been recognized as the intersection of these two areas is critical. And so we were wanting to address that problem. Now, maybe that's a little abstract to say what is a cyber-physical system. So let me give a different kind of approach. So within the Link Lab, we have a lot of work going on, and we kind of bring it into three areas. And one is smart cities. So it's easier to understand what a smart city might look like. So it's going to handle congestion, transportation, traffic, emergency response, pollution, noise, and so on. And so if we can install systems in cities to make them more livable, we have smart city is a cyber-physical system. Secondly, we do smart health. Right? And so smart health, the idea is we're going to put wearables on your body, in the area to make your health better and you live longer. Right? And so that's whole smart health direction is also cyber-physical systems. And the third is our autonomous systems. So autonomous systems, the most common ones are things like self-driving cars or drones or robots. And we can make these into even cognitive assistants using a lot of machine learning. So those are three kind of general research areas that many people in the lab are undertaking. The second question is, how did this lab come about? So I would say there were maybe 5 or 6 of us, or maybe 7 faculty working in this area, but we were fairly disjoint. We were just doing our own thing, and maybe we had pairwise interactions. And Dean Benson arrived, and he asked for proposals on multidisciplinary research and where the future is going to be. And so we got together and wrote a proposal on that, and we were fortunate enough to get it approved, and we were assigned 8 new faculty lines. We hired 7 of those 8 already, and when we had the original 7 or 8 of us, plus those 7 or 8, we got to 15, but it was so infectious that other faculty started getting involved, and now we have over 30 faculty in the Link Lab. And as was mentioned earlier, we have close to 100 graduate students. So this is exciting. And then the second thing that happened was the Strategic Investment Fund from the university level came into focus, and they said submit proposals. So we submitted a proposal for a renovation of Olson to house a multidisciplinary research space called the Link Lab. And so we got $5 million to do that. And the lab is now completed. We had an open house for it, a kickoff in February. We had drones fly in the ribbon for the cutting, and we cut the ribbon. Okay, so drones are useful. And after this panel, if you would like to follow me over there, we can walk over to the Olson Hall to do a tour of the Link Lab if you're interested. It's not too close, but it's right near the football stadium. You're welcome to come. Please, at the end, if you come up here near the podium, we'll get a group together and walk over. Okay, so now with that, let me introduce our first speaker. We have 2 speakers, each going to give short presentations, and then we hope we will have lots of time for questions. All right. So the first speaker is Ben Calhoun. He's actually a UVA grad, and he was an electrical engineering grad. And he went to MIT for his PhD. We won't hold that against him. But anyway, and he's going to give his first talk on self-powered chips.
Good morning, everyone. My name's Ben. Very happy to be here. Like Jack said, I'm an alum, like many of you. I graduated from UVA as an undergrad in 2000 from the electrical engineering department. And of course, I had to come back and work here because I liked it so much. So that's what I did after I got my PhD. I applied to come back to the faculty at UVA. I applied to exactly one school, and here I am, and thrilled to be here. So I've been on the faculty since 2006, working in integrated circuit design. So I'm going to tell you a little bit about chips, integrated circuits, and some nerdy stuff related to that. And then I'm going to also try to connect the nerdy technical work that I do up to the application level and give you a sense of why it's really transformative, how it fits into cyber-physical systems and the Link Lab, and why you might care about it in the future. So this graphic is one of many like it that expresses an idea of something like Jack was talking about. What is the future going to be? Smart environments. And in this particular graphic, you can see it calls out a lot of different categories. Manufacturing, what does smart manufacturing look like? It might look like supply chains and conveyor belts that know before failures when a component is going to go down so that people can predictively schedule maintenance rather than dealing reactively to things that go wrong. Smart government, I don't know if that's going to happen. I don't know if technology can really help with that one, so we'll skip that one. Even better connectivity and communication, Wi-Fi and mobility, networks that span everywhere. We're used to connectivity with our cell phones, but in next generation, almost anything, objects and environments are going to be connected and able to communicate with one another. Smarter citizens, Jack mentioned the concept of smart health, and we see that over here too. The idea that we can measure far more information about your health so that we can, again, predictively anticipate things that are going wrong and provide care that's far more attentive than currently, where usually you only get access, a doctor only gets access to what's going on with you when you're actually sitting in front of him or her, and that's pretty rare. If instead we could continuously monitor things about you, then we could potentially dramatically improve physicians' abilities to treat you or to benefit your well-being even before you have problems. Smart farming and agriculture, I've talked to people who grow grapes, who currently have a single monitor in their entire vineyard, but who say, what I really need is a sensor on every vine, because there are microclimates down to that level that really affect what's going on in the plants. I've talked to people who grow vines who want to use sensors to listen for the crunching sounds of chewing beetles so they can tell when insects are there. But this is a problem. There are a lot of vines in a vineyard. How do we solve that kind of problem? Smart buildings, we do a lot with monitoring up spaces so that spaces are smart. You know, really simple examples of this are motion-activated lights. You don't need the lights to be on if you're not in the room. Microclimates where you change the environment, the HVAC, to be attentive to how many people are in a space. You put this many people in a room, after a while it starts to get a little hot, that kind of thing. Smart energy, this is a big one for security purposes as well as efficiency. And Jack already mentioned smart transportation, which becomes a real problem in cities. All of these visions deal with smart, smart, smart. And smart comes from a lot of things. You have to get information, analyze it, and understand it, and then act on it. And the part of that problem that my work addresses is in the getting of information and then the initial processing of it, providing it back into the big data cloud where machine learning can act on it. Machine learning algorithms are only as smart as the data that they're operating on. So, how does that relate to circuits, you may ask? Well, this slide shows a plot of the growth of products that come from what's been happening in the semiconductor industry. You might not be that familiar with the semiconductor industry, but you certainly have benefited from it, and you've probably bought the products on this graph. So over decades, because of exponential growth in the semiconductor industry, there's been an explosion of the number of electronic devices that are available. Back in the 80s, employees at large businesses might have a computer, but that's about all the computers that were out there. Then we grew by about an order of magnitude, and every professional had a laptop. Then we went to every home having a computer. Now every person in this room has a very sophisticated computer that also happens to be able to make phone calls in your pocket. We have moved even beyond that to this age of mobility where you might also wear one or two smart widgets, like a watch or a Fitbit or some sort of physiological tracker. So that's where we are today with what people are starting to call the Internet of Things. A lot of devices, about 1 or 10 per person, connected to the internet and providing information. All the information and data coming from those devices today are to some extent kind of human generated. You know, you're typing stuff in, you're taking pictures. The vision for the next computing revolution is that there will be an even larger explosion of devices that are not tied just to people and the data that people generate, but that instead are collecting information passively from the environment, from your body, from infrastructure, from roads, from cars, from vehicles. That vision of the next generation Internet of Things is predicted to have 1 trillion or more nodes, wireless sensors, that are distributed around almost invisibly in the environment that are collecting tons of new information and allowing all those systems that I was talking about to become smart. There's a problem. 1 trillion is a big number. So let me give you a sense of what I see as the biggest barrier to getting to 1 trillion node Internet of Things. It's a nerdy semiconductor problem. You've got to provide power to all of those things. And right now we do that with batteries. You know, your Fitbit has a battery. How's that going for you? You got to go plug it in every week or so, right? And it's annoying to go plug it in, and after you've plugged it in 4 or 5 times, you might not pick it back up off the charger because it's inconvenient. Well, battery life is really limited these days, but let me be generous. Suppose I give every single one of those trillion devices a 10-year battery. Totally impossible with today's technology, but let's do it anyway. 10-year battery for every one of those trillion devices. We would still need to change 274 million batteries a day, even with 10-year batteries. That is not going to happen. So we figured out a long time ago, Batteries cannot power the trillion-node Internet of Things. We believe it's inevitable that we need to get there, but in order to get there, we have got to get rid of batteries. So I'm an anti-battery guy. All right, so how are we going to do that? Well, we have to throw some technology at the problem, and we can benefit from the very trend that has exponentially contributed to the scaling of electronics. But let me tell you what we need to do first. It's a challenging problem. So this is a bunch of numbers. I'm not going to read them all to you. The top table tells you how much power is consumed by some electronics that you might be familiar with. A laptop burns a few hundred milliwatts. And just for those who haven't paid attention to these prefixes, a watt is a measure of power. A milliwatt is 1/1000th of a watt. A microwatt is 1/1,000,000th of a watt. And a nanowatt is 1/1,000,000,000th of a watt. So each new prefix is 1,000x different from its neighbors. So a laptop is a couple hundred milliwatts when it's idle, doing nothing, and it's several watts when it's active. Your iPhone is similarly a couple of watts when it's actively making a call or streaming video, and it's still 100 milliwatts when it's off, idle. Even your wristband wearables that are supposed to be really low power, they burn something like 1 or 20 milliwatts when they're active, particularly when they're wirelessly communicating with radios. It takes a lot of energy to send electromagnetic waves over the air. So how do we get rid of batteries? Well, the obvious answer is let's harvest energy. You know, people are trying to go to solar for big grid power. Can we do that for tiny things? Well, you can, but the amount of energy available to harvest is pretty small. So no matter, outdoor solar gives you a lot of power, but all the other kinds of things you might want to harvest from, indoor light, like in here, thermal gradients, a difference in temperature, vibration, motion, RF energy, all of these sources of power tend to give you about 10 microwatts per square centimeter. So that's 1/1000th of the amount of power you need for today's low-power wearables, okay? So we need to burn about 10 milliwatts of power to do something useful with the electronics that you can buy off the shelf, but we only have about 10 microwatts. That's a 1,000x difference. So let me give you an analogy to give you a sense of how hard this problem is. Let's say we made a 1,000x improvement in the efficiency of your car. Right now, maybe it gets 30 miles a gallon. If we improve that by 1,000x, it would get 30,000 miles a gallon. You could fill up the tank once and never have to get gas again for the lifetime of the vehicle. That's the kind of improvement we have to make to electronics. That's a big change. It's a big challenge. So can we do it? Well, yeah, we already did it. It's pretty awesome. That's one of the things going on here at the University of Virginia Engineering School. So I'm going to give you 2 examples of chips that graduate students working with me and with my collaborators have built that did this. We got the 1,000x improvement. So this is a system on chip. That's a dye photograph of what we call the dye, the little piece of silicon with a bunch of transistors on it. It has about 5 million or so transistors on it that my graduate students designed how they all work together to do this function that I'll tell you about. And the total power consumption of this chip is 20 microwatts, 19 microwatts, when it's active. So we brought down from 20 milliwatts to 20 microwatts. That's 1,000x. What does this system on chip do? Well, we built it for wearable biophysical monitoring. It can measure your electrocardiogram, which is your heart waveform, electroencephalogram, which is your brain waveform, and electromyogram, which is muscle activity. It can do any of those. It interfaces with your skin and collects those signals. It converts them, it amplifies very small voltages, converts them into ones and zeros. It has processors on the chip that can calculate every heartbeat and monitor for things like cardiac arrhythmias. It can detect atrial fibrillation, which is a very common cardiac arrhythmia, in just a few beats. And it includes radios that can communicate and stay in touch with an adjacent system like your cell phone. All of that for 20 microwatts. And we powered it. It also includes the circuits that convert the difference between your body temperature and the air into usable energy to power the thing with no battery. That was in like 2012. We've been working on it for a while, and this is our newest generation that we published last year that's a similar design, but it brings in some other chips to store information with no power when we need to totally power down the system, and to communicate more efficiently directly with a phone using a Bluetooth-compatible transmitter in these adjacent chips. You can see 3 chips packaged up in a single package sitting on that penny. We brought the power down from 20 microwatts to half a microwatt for the core SoC, so we can do even more for these minimal power budgets. So that's the kind of work that we're doing in integrated circuits, and I gave you a sense of some of the applications, particularly around wearables, although we're using this system for lots of other smart Internet of Things, cyber-physical systems applications as well. And now I'm going to turn it over to my colleague to talk about some of the higher-level applications work that we can do with these kinds of electronics.
Great. Thanks, Ben. You can see why we hired him back here to UVA. That was pretty exciting things that are happening there in the ultra-low power circuit space. So my name's John Locke. I'm a professor in the Electrical and Computer Engineering Department. I came to UVA back in 2000. It's been such an exciting ride here, and I'm really excited today to tell you about the work that we're doing in smart health and in the area of cyber-physical systems in the Link Lab. So this is really sort of the vision that we have for smart health, as Ben described, having all of these sensors that are attached to us or embedded in our environment, and thinking about ways that we can use that to improve our own health and well-being, lower healthcare cost, living longer, healthier lives. So I'm going to tell you some specific examples of that, but I'm going to start by telling you about my mom. So my mom, when she was in her late 60s, she was diagnosed with systemic scleroderma, which is a hardening of soft tissue. It affects different people in different ways, but for her, it primarily affected her lungs. So her lung capacity started to drop over time. She had to start to use oxygen all of the time, and really, decreased mobility, decreased energy, all of these things. But it was in the last about 2 months of her life or so where her oxygen capacity, her breathing capacity dropped so much that it really started to sort of drain the oxygen in her brain. So she started to exhibit various features of dementia. And one of the kind of key aspects that is really common and is a really kind of unfortunate side effect of dementia is are some behavioral issues. There's a lot of agitation that is commonly associated with dementia. So as somebody who works in the smart health space, as you might imagine, I was brainstorming for years of ways that I could help my mom. Could I develop a new kind of sensor? Could I figure out some kind of signal processing technique? Working with people like Ben and Jack. Could we really help? And I would talk to her doctors about it and really try to do this kind of brainstorming. But they all agreed these types of autoimmune disorders like scleroderma are just really, really tough nuts to crack. So that was kind of frustrating as somebody who works in this space. But now let me tell you about my dad. My dad, Fred Locke, was an incredible 24 hours a day, 7 days a week caregiver for my mom. And this is a really common situation. You probably have seen this in your own families or in friends in the community. It's these family members who care for loved ones as their health is failing. And it's amazing. I mean, they aren't getting paid for it. They're doing it out of love, out of devotion, out of affection. And it's really sort of an amazing thing as I watched my dad, step into this role of caregiver for my mom. I mean, she had done this amazing job taking care of all of us for all these years. And now here was my dad playing that role for my mom. And they just lived right down the street from me. So I was able to see this very intimately. But the amazing thing is my dad never once complained. All those years taking care of my mom, I mean, he just was a trooper throughout and always had a smile on his face. But in those last couple of months when my mom was starting to struggle with those symptoms of dementia and those sort of behavioral issues started to come into play and some agitation, especially in the middle of the night, as my dad, who, he needs his sleep as well, was really starting to struggle with them. And he kind of pulled me aside and said, John, I don't know if I can do this anymore. I want to so badly, but it's getting to be too hard. I don't feel like I can do it. And that conversation really sort of stimulated some thinking for me of, well, maybe I can do something for my dad and people like my dad who are, trying to care for loved ones at home. So I'm going to come back to that in a second. But first, I'm going to tell you a little bit, kind of pop up a level now, to think about smart health, the smart health paradigm in cyber-physical systems. And what it is that we're really trying to do in this space. And there's lots of different applications, and I'll give you examples of some of them. But that capability to be able to sense what's going on out there in the world, or what's going on with you as an individual, or with a group of people who are interacting with each other. Being able to detect critical things that come up, and then maybe even ultimately predict certain kinds of conditions before they even begin. And then, if we can do all of those things, can we then intervene in a way that is effective, that is helpful to us as individuals or even us as a society as we deal with issues of health and well-being? So this is really where cyber-physical systems and the kinds of things that Jack and Ben were talking about come into play. So for sensing, there's a whole list of things that we can do with this combination of cyber and physical. Ben talked about low-power circuit and system design, or wireless communication and networking. This Internet of Things concept. And this really important issue, humans are in this loop too. Humans are part of these cyber-physical systems. So thinking about the human factors aspects of this. So we've made great strides in this. Ben described some of the things that he's done along those lines. And of course, this generates a lot of data that if we want to start to detect and predict things, there's lots of innovations that we can make in signal processing, in machine learning, artificial intelligence. This realm of data science is really becoming quite important, and that's all tied in to the cyber-physical systems loop here of sense, detect, predict, intervene, and then feedback. And then so for those interventions, there's lots of different ways. Once we collect this data and make sense of it, we can create these models. We can develop these feedback control mechanisms. And again, with human factors being a key aspect of that. Now, something else that comes up that's quite critical as well is this issue of security and privacy. These trillion things that are going to be out there, how can we collect data and make sense of it in a way that isn't violating people's privacy? And how do we prevent people from hacking into it and actually, making these systems behave ways different than they're intended? So these are all some of these core capabilities that we have in the area of cyber-physical systems that we work on in the Link Lab. And then doing that within the context of these really, sort of societal grand challenges, and some of the ones that we're tackling, as Jack mentioned, of smart cities and autonomous systems and smart health. So in the realm of smart health, so for sensing, again, there's these things that we can do in terms of these wireless capabilities and mobile and wireless and various types of wearable devices, these massive scales, these trillion node kinds of scales that we're talking about, and thinking about what we can do in terms of sensing health with those kinds of capabilities. Self-powered as another great capability, as Ben mentioned. And what are some things that we can do? How we can make our wearable devices, even smaller if they don't have a battery, and how much more likely people are to wear them over extended periods if they don't have to charge them on a regular basis. In terms of detecting, there's lots of different applications we're working on in the Link Lab where we're partnering with people all across grounds of things like, and being able to have those capabilities like detecting eating or detecting stress or some critical health events like atrial fibrillation, as Ben mentioned, detecting falls in the elderly. I mean, all these kinds of things are become very real capabilities as we build out these cyber-physical systems. And then similar to prediction, if we can actually sort of figure out, well, what are the kinds of things that lead to some of these critical health events that we're interested in not just detecting when they happen, but predicting when they might happen so that we can then intervene to prevent them from happening. So that's a real critical aspect of this as well. So those interventions then can come in a variety of forms. A really interesting one that some of you may have heard about that's developed here at UVA is the artificial pancreas for type 1 diabetics, of being able to detect and ultimately predict these fluctuations in glucose levels in the blood, and then dispensing insulin automatically based on those models. And one of the projects actually that I'm working on with Jack, as well as some behavioral psychologists, of looking at things like family eating dynamics. So not just what people are eating or how much, but where, when, with whom is the television on, what interpersonal stresses are going on within a family there that might have a downstream impact on diet and activity. So we're working on that within the context of childhood obesity. So there are lots of these different kinds of things that we can do. Once we build those core capabilities of cyber-physical systems and partner with our various people around grounds who work in these health application areas, we can really have a tremendous impact. So with that, let me get back to my parents here again, and how is it that I could use these kinds of capabilities to help people like my dad? Well, so in working with some people in geriatric psychiatry and geriatric nursing, and trying to really understand this issue of agitation in dementia patients, is that we realized that if we could really detect the early stages of agitation, that could really be powerful. Or that if we could understand what some of the environmental and contextual factors are that might actually lead to agitation. So if we can create sensing technologies that are worn by the individuals and embedded in the home, that we could detect those early stages of agitation and then develop these models where we can see what some causal factors might be. What are some of the things that might actually lead to agitation in a dementia patient? And with those capabilities, if we can detect the early stages of agitation, we can provide a real-time notification to the caregiver so that they can intervene before agitation escalation. So there's typically a ramp-up phase for some of these agitated behaviors. So if the caregiver can get to their loved one early enough, can prevent agitation from really ramping up. And then, of course, if we can then figure out what are some of those causal factors that lead to agitation in a particular patient, when we detect those conditions, again, we can provide a real-time notification to the caregiver so that they can alter the context or the environment to prevent agitation from even beginning. So we've been working on this project now for a number of years, and actually just last month, we turned on the switch that is now providing these automated notifications to the caregivers. So these sensing systems and these feedback capabilities are now embedded in the homes of a number of families who have a loved one with dementia living at home. And we're really hoping that in the still fairly early stages of this study, but that we're going to get the kinds of results that are really, really going to improve the lives of the caregivers and really empower them to be able to continue to care for their loved ones at home, and which I think would have made a huge difference for my dad as well. Now, of course, as we think about what's necessary to do work like this. I mean, I'm an electrical engineer. What do I know about geriatrics and dementia? Well, it's through these kinds of partnerships that we're really able to make a huge difference. And so I mentioned we're collaborating with people in geriatric nursing and geriatric psychiatry. And to be able to forge those kind of partnerships at a great comprehensive university like UVA is something that's very special here. It's certainly something that drew me here as a faculty member. And being able to just walk across grounds, find those kinds of partners, so that as we're developing these core technologies in cyber-physical systems, to engage with domain experts so that we can address these societal grand challenges is something that is very exciting. It's incredibly personally rewarding. It's something that gets our students really actively engaged. And I think it's something that is really going to position UVA as a tremendous leader as we go forward into the third century of this amazing university. In fact, a really interesting statistic of part of why I'm so optimistic about all of this is we did this analysis. So there are depending on how you count, there are about 368 engineering schools in the United States. Of those, there are only 2 universities that have an engineering school and a medical school that are both ranked in the top 40 in the U.S. News and World Report. Of those 21, only 8 of them have the engineering school and the medical school within 1 mile of each other. So, we're in that 8. So we really, having the kinds of capabilities that the 3 of us have talked about today in cyber-physical systems, in being able to take a 10-minute walk across grounds and meet with world experts in areas of health is something that is, has made a tremendous impact on my career and I know my colleagues' careers. And as we go forward, I think that the potential is really just completely unlimited. So thanks for giving us the opportunity to talk with you today. And I know that we'd be thrilled if you had any questions or ideas for us to share as well. So thanks so much for your attention.
We should move it.